Everyone. In the last video, we have talked about the basic structure of an NLP project. So in the next couple of videos, we will discuss about different text pre-processing techniques, which will result into the vector, the matrix, the feature matrix, which will be fed into the model. So for textual pre-processing, we have some techniques or algorithms, out of which some are necessary, some depends on which kind of problem statement we have in our hand. So for we have text normalization, tokenization, stop word handling, stemming and limitation. So in tokenization, there are two kinds of tokenization available. One is word tokenization and one is subword tokenization. If it is a word tokenization, then we need to do all these things. We need to handle stop words, we need to do stemming and limitation. But if it is a if it is a subword tokenization, then we don't need these two things. Okay, but in case of text normalization, we need both of them. I mean, this is required in both of the cases. So what is exactly text normalization? This is very simple. So whenever we have a sentence, right? So suppose we have uh, the boy is riding a bike. So you see this punctuation mark, full stop, and maybe if it is a question, if it is a interrogative sentence, then we would have got a question mark instead of a full stop. So all these punctuation marks and those punctuation marks and all the unnecessary symbols, like if we have a sentence like I have $50 in my pocket. So in this case, this dollar sign is a unnecessary symbol, is an unnecessary symbol. So these punctuations and unnecessary symbols will be removed from our text. Why it is being removed? Because these are redundant things. See, these dollar sign or question mark, full stop, these doesn't hold any information in case of uh, with respect to our model, right? So that's why we don't want to crowd the information matrix, feature matrix, with these kind of redundant things. Also, we are going to normalize the words. What do I mean by normalize is that we need all of them in the same lowercase, so that there is no ambiguity. So suppose, here we have a capital letter, starting the sentence with a capital letter. So we will reduce it to small letter, so T, and here we have I. So this kind of basic pre-processing we will do in case of text normalization. And after the input text is normalized, we can go into the tokenization part. So let's jump into tokenization now. So as we have discussed in the last video, that word tokenization is basically responsible for vocabulary creation. So this is the main motto of our technique. So in case of tokenization, we mainly follow these two things. One is word tokenization or subword tokenization. If you are talking about word tokenization, is very simple. All we need to do is we need to split our input text with respect to white space. Because see, like the boy is sitting. So in case of these white spaces, will separate words, right? So if we want just the words, we can just use the space in between and separate the sentence, split the sentence based on these spaces. So the reduced sentence will be like this: the boy is sitting. So it's very simple, but this word tokenization is somewhat old. Okay, this is old technique, and also this technique has got a lot of shortcomings. So what kind of disadvantages we have got for word tokenization? So you see, word tokenization has two major drawbacks. Let's take an example sentence for it. The runners are running towards a runnable path. Like, this is the uh, these are example sentence. It is quite uh, mm, I mean, quite unusual, I know, but it will help understand how it is, how word encoding can cause a lot of issues. So immediately we can see by looking at the sentence that there are some similar words like runners, running, and runnable, right? So when these kind of similar words are there, uh, we can we can see that there are some common subwords like run is repeating in every word. In case of word tokenization, what will happen that in the vocabulary that we will be creating, we will have all these words like runners, uh, running, runnable. So we will have all these three words, but this run part will every time occur and its space. So you see, this is one of the main issues of word embeddings. There are a lot of redundant space eatings. So that is one thing, and the other thing is, uh, suppose this is our vocabulary, and our computer buddy is now looking at this new data where we have the word run. Now this is the this is very basic word, and I mean, the computer won't understand this word, as in the vocabulary run is not there. And even if runners, running, runnable, all are very similar to run, it will completely miss out on understanding what is this actually. So that's what that's what the two major shortcomings. And by the way, these words which are not present in the vocabulary, these words are called out of vocabulary words. So OOV words, which is out of vocabulary words. This kind of out of vocabulary words will be coming lot more in case of word embedding, word tokenization. So that's why we are moving to a better methodology, which is subword tokenization. So in case of subword tokenization, how do we generate the tokens then? We generate the tokens using latest statistics. So latest statistics is something that is very powerful. It looks at the frequency of letters in our corpus, and it will club them together to keep the most frequently occurring subwords. So, like, suppose you have this iceberg word, and if we are seeing iceberg in our corpus, we will try to see how many times ice and berg are occurring separately. And if it is if there is sufficient amount of time ice is occurring and berg is occurring within a word, then we will tokenize ice as a separate token and berg as a separate token. So that will give us better handling for out of vocabulary words as well. Suppose, like, we are getting some other word in the test set, we are getting, suppose, ice cream. So the computer doesn't know ice cream because ice cream is not there in the vocabulary, but at least it will get the idea that ice is there in the vocabulary, so it will identify the ice part of the ice cream, and it will know that this is something related to ice. So that's the best part about subword tokenization. That's why subword tokenization is used quite often in a lot of big LLM architectures, basically in transformers. So we have three major techniques, algorithms for subword tokenization: byte pair encoding, unigram language modeling, and word peace. So we will go through the byte pair encoding part, byte pair encoding algorithm theory today. And in the next video, we will see hands-on from scratch implementation of byte pair encoding as well. So yeah, let's jump into byte pair encoding now. Let's consider a corpus text because that will work as our example corpus, and we will understand how the algorithm is breaking it up and generating the vocabulary as well from it. So we have taken this corpus: crazy, 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 crane, crane, dance, dance, pan, pan, game. Quite a crazy corpus. I mean, this is not a typical size of a corpus, but this is for our simple simplicity of our understanding. So the very first step that we will do in case of BP, we will call byte pair encoding as BP from now on. So the very first thing that we need to do, we need to initialize our BP vocabulary. So this is our BP vocabulary that will be populated with all the different tokens that will be generated through this algorithm. So how we are going to initialize it? We have two options. One is we can initialize it with all A to Z letters, or we can just take the unique letters that are occurring in the corpus, and we we can just append an unknown token. See, whenever we are using only unique letters in the corpus, there are chances that some letters are missing in the corpus. Like suppose y is not has not occurred in the corpus at all. So it is very, I mean, it's very low chance, but still it's not zero. Like the probability is not zero. So uh, in those cases, whenever a letter is not present in our vocabulary, we need to have an unknown token for it to handle the out of vocabulary letters, and that's why this unknown token is appended. After we have initialized our BP vocabulary, we will now go to the corpus vocabulary and we will create a dictionary which will store all the different counts for different words, and the words will be split into tuple of characters. So simply put, you see crazy has occurred three times in our corpus. So crazy has split into different letters, and at the end of the word, to symbolize where the end is happening of the word, we have kept a underscore. So if we see y underscore repeating a lot of times in our corpus, that means a lot of words are ending with y. Got it? So crazy has got is repeated three times in our corpus. Crane is repeated two times in our corpus. Dance is repeated two times in our corpus. Pan is repeated two times in our corpus. Game is repeated one time in our corpus. So this is our step two, and after that we will go to the heart of BPE. So step three and step four is literally the heart of BPE. What exactly we are doing here? This is where we are populating our vocabulary. So in the corpus vocabulary, we will take consecutive character pairs. So consecutive character pairs we need to pick. So from crazy three, so crazy, from this crazy word, we will just pick consecutive pairs. So CR, RA, AZ, ZY, Y underscore, right? From crane, what will it be? CR, RA, AN, NE, E underscore, like this. So basically in this fashion we will consider all the consecutive pairs and we will get the frequency in our corpus. So suppose CR, so CR together, I mean C and R consecutive pairs has occurred how many times in our data set? You see, in crazy CR, in crane CR, but nowhere in the other words. So only in those two words, and crazy has occurred three times in our corpus and crane has occurred two times. So in total CR has occurred three times and CR has occurred two times, so total is five. So CR has occurred five times. What about array? Array is the same. Array, crazy array, crane array, dance, pan, game, there is no array. So array is also 5. ZY has occurred only in crazy but not anywhere else. So that's why for ZY the count is 3. The frequency count is 3. So in this way, after getting all the counts for consecutive pairs, we will determine which consecutive pair has got the most count, meaning which is the most frequent occurring letter pair in our corpus. So in this case, we will see that AN is the most frequent, AN here, and AN here. So crane, dance, pan, these are the three words that AN that has got AN, and each of the words has two frequency. So all total AN has occurred 6 times. So in this way, we will know that which is the most frequent subword. We can call this character pair as subword, which is the most frequent subword in our corpus. So in the next part, what we can do, we can just combine this pair together. You see, AN is occurring multiple times in our corpus. So it makes sense to keep the AN together as a single character, as a single set of characters in our vocabulary, right? Because possibility is that in the test set also, in the unknown data that model is going to see while generating embedding, AN will occur frequently there also. AN together will occur there also frequently in the training data. So that's why it makes sense to keep these together as a single token in our vocabulary. So that's what exactly we are going to do in our step 4. We are appending AN in BPE vocab. So whatever BPE vocab we created in the step 1, A to Z or unique letters, we are going to append now this most frequently occurring character pair in the VPE vocab set. We are also going to do another thing. We will change our corpus vocab a little bit. You see, once we have got that AN can be merged together, there is no point of keeping AN as separate character entities. We can just merge it in the corpus also, and we can keep it as a single entity. So that's what we are going to do. So crazy 3, but in case of crane, we are going to have CR then AN as a single character, then E, then underscore, like this. Sorry, here I forgot to edit. So here also, in case of dance also, we need to have a single character. So dance DAN as a single character, CE underscore. In case of pan also, PAN as a single character, then underscore. And the next step is we are going to repeat this process again. So now you see, one might be confused that AN has already got the most number of frequency here. So in the next time also N will get the most frequent pair award, right? But no, it will not happen, because now our corpus vocab is updated, and this corpus vocab is now updated with the AN combined pair. So next time when we are considering this pair thing, consecutive pairs, AN will not be a consecutive pair, because AN now is a single character. So next time what will happen, AN and E will be a consecutive pair. Here AN and C will be a consecutive pair. P and AN will be a consecutive pair. So now the subword length will be increased. So in this fashion, the more you keep repeating this loop, this step 1 to step 4 repetition, the more the subword lengths will be increased, and we will see the frequency of those bigger length subwords will be decreasing over time. So we can, this K is a parameter of BP algorithm. There is no fixed, fixed number or optimal number of iteration. It depends on your corpus, and it depends on the problem statement you want to solve also. So I prefer it around 500 to 1000 times, because in that fashion what will happen, most of the frequently occurring subwords will be captured in our vocab. There will be some words which will have less frequency but still included in the vocab. But anyway, those will not be coming in our training data frequently, because those are less occurring words, right? So that's basically the vocabulary generating part. And also one thing I forgot to mention, so when we are building this character pair counts, and we are merging this characters which have occurred which has occurred most frequently, we need to also keep a BP merges dictionary, where we will store the character pairs that we are merging with their maximum frequency. I mean, with the frequency they have got. So AN has got 6, which was the maximum frequency. So we are going to just do AN colon maximum frequency, which is 6. In this fashion, in the next time, what will in the next loop, whatever pair will come, that will also be appended next to it. Why we are keeping this merges? You see, the consecutive pair that we are combining together, those pairs are kind of like a rule, because we in the training data also, whenever we are saying an, we are going to combine them, right? Because we have got that in our vocabulary. Now BP algorithm tells us that when you are using this vocabulary to tokenize another set of data, mainly your training set, you need to follow the order of follow the order, the way you have learned these pairs. What I mean by that, let's see another example. So in this portion, we will see how to tokenize tokenize another set of data using this vocabulary. So we will follow a greedy approach. How we are going to do? Step 1, the words are split in single letter characters. So whatever we did at the first, when we are creating BP vocab, we are splitting the corpus into unique letters. We are going to do the same thing. So we are going to split it in single letter characters. So suppose sand is going to be tokenized, and for sand we are just splitting the sand into single characters. So SAND. Now what we will do, we will scan through the letter list, and we will see that what is the which portions of the word can be merged together according to our rule. So this is the BP merges dictionary that will be generated from this corpus. I have just copied it from our code that we will be seeing in the next video, the implementation. So here you can see AN is learned first. So we need to combine AN first whenever we are seeing AN. So even if there are some CR present, we will not combine CR first. So suppose we have like suppose this see this part, a CRAN. So suppose we have CR up in front of A. Suppose we have some letters we have. So letter, and then we have CR, and then we have A, then we have N, and then other letters are there in the word. Okay. Now what we'll do, when we are scanning through it, we will not combine CR first. We will ignore CR and we will combine AN, because AN is the first thing that we have learned, first merge compared to CR. So once we are done with AN, we are going to scan through it. Let's say we didn't find any AN here. Now we are going to scan again, and now we have found CR, and CR, all the ANs are merged. So next time we can merge CR together. So in this fashion, what happened? See, this CRAN didn't get a chance to get merged. If we would have followed the simple approach that scan through that word, and whenever we find two letters which are merged together in our vocab, we can just merge it. Then CR would have merged before AN, right? So once CR merged, it would have been CRAN. In the next time, CR and A will be scanned together and CRA will be merged together. But this didn't happen. Instead, we got two separate tokens, CR and AN. So this is the most important part of BPE. We need to merge the letters based on the based on the merge rules in the order that we have learned them. So hopefully I explained BP algorithm properly. So now we are going to look at some most useful properties of BP vocabulary. I mean, why we are going into the subword vocabulary. We will see that this, as I said before, that stop word and all the other things, this lemmatization and stemming, these are not required. We don't we I mean we have not discussed lemmatization and stemming yet, stopword also, but these are not very complicated concepts. For stopword is basically most frequent words like articles or verbs, this kind of thing. So it like a, in, the, is, these doesn't hold much information about the text, but these are very frequently occurring words. I mean, these are very frequently occurring words, that's why it doesn't hold much information, right? So in case of in case of BP, as these are very frequently occurring words, it easily captures them in the data, in the vocabulary, and it keeps the a, in, the, is, these as a as separate tokens. It doesn't break it up because these are occurring together frequently. Also, it will include a lot of common morphemes. What do I mean by morphemes? Morphemes are smallest meaningful constituents used in a word, like es, er, est, like smallest, largest, tallest. So er, smaller, taller. So all these small suffix or prefix, which are added to the word to make the word to convert the word form, those will be used with a lot of different words as well. So it will frequently occur in the corpus. So that's why these will also be included in the PP vocabulary. What will happen in that case? Suppose we will. What is the advantage? Like suppose we have a word which is weirder. Now this weird word. Suppose this weird word is not present in our vocabulary, but this er will be present in our vocabulary. Why? Because this er has got really small, I mean, this is the this is a morpheme. I mean, this has been used with a lot of words, so that's why this er will be appearing in our vocabulary. And I mean, the computer will be able to tokenize or prepare an embedding for this er part, though it will not figure out what is this weird word, but it will figure out that this is something that is a that is giving me a comparative uh, this word is doing a comparison, like this is something is weirder than something, so it is doing a comparison. It will understand that based on this er part. And this is exactly why BP works like a charm, and it is used in a lot of LLM models like GPT, Roberta, BART, Tiberta. All these different algorithms we are going to learn in future, but hopefully I could explain I explained the concept of VP and how it's working in the backend pretty clearly. If you have any question, please comment down below. And next in the next video we will see how to implement BP vocabulary in Python from scratch, and we will see how it is working on a Wikipedia corpus, and we will see how it is tokenizing tokenizing different sentences. See you in the next one. Thank you.